talk about the, does not work on this version. Hold on. Let's see. Okay, well, let's go in. Let's talk about the midterm. So we're going to have to curve that, because although some people did quite well, a number of people didn't. So we're going to curve it to have a mean of 82 or so and a standard deviation of 10. That's going to give 100 to the highest score. But that doesn't necessarily mean that we exhibited enough progress toward our goals of learning this stuff. And although this material is challenging, the midterm shouldn't be the place where the challenges come up. Challenges should hopefully be dealt with and addressed and answered and whatnot before midterm happens, and then the midterm is an opportunity to ask questions about, what we've already covered, multiple times. But nevertheless, some people are going to struggle on the midterm, and that would be okay. What's not okay, really, in my view, is to have, well below one question per week asked on ed discussion, and then compounding that with, not showing up to recitation sessions, not ever, getting your stuff sorted out in office hours, and then you get on the midterm and have difficulty answering, any of the questions when you had plenty of opportunity and, it's incentivized with your participation on a discussion to ask those things beforehand. And so, particularly for question 1, that's kind of the culmination of the first part of the semester. I mean, we learned all this stuff about probability. We learned how Bayesian analysis differs from, particularly frequentness analysis, other forms of analysis. We learned a little bit about how MCMC works in STAN, even though we're not asking, questions about the physics. And then we get to linear models, and we can do those with MCMC. And that's not really the most case where, you're going to get hugely different answers from if you did, frequentness thing between the posterior medians and like the OLS estimates or something like that, but we can do it with MCMC, and we get posterior draws and, be able to do that. But even more fundamentally to updating your beliefs about the parameters or any of the unknowns, it's having beliefs about the parameters and the unknowns to start with. And that's really kind of chronologically more fundamental to Bayesian analysis than updating your beliefs with Bayes' rule, is having a model, a generative model that you can simulate from, where for every unknown parameter, you're substituting lots of draws from a known probability distribution. And you can plumb those through your generative model, and that's something we've done about a dozen times between the lectures, the homeworks, the recitations, all that. And so to still be having trouble with that idea or the code for that, once you get on the midterm, is a problem, because that's the sort of thing that we're going to be doing with a bunch of different generative models as we go forward the rest of the semester. And so for that very first problem, you could have pretty much just copied the code that did, drawing from the linear model from the lecture or from the recitation, a couple of days before the midterm, just like change the variable names, and it would have run, or it should have run, something like that. And so, based on the previous data, you ought to be able to choose decent priors, keep the distribution of the predictions between 0 and 100 for the most part, then, update it, use the posterior draws to answer the question, what's the probability proportional representation systems have more turnout? than plurality rule systems, and sort of irrespective of your priors, you should have gotten a very high probability of a positive effect. And even though it didn't ask you directly, you should be able to mentally contrast that with what a frequentist estimate or t-test would tell you, which is, what's the probability of observing an effect larger than this, given that the effect is 0, and rejecting that null hypothesis in favor of the alternative hypothesis that is positive. Bayesian gives you much more intuitive and harder to misinterpret answer to the substantive research question. And so on. And then you can do some posterior checks to see if linearity is reasonable over that interval and whatnot. But it's, again, important that you have prior beliefs, because it's not like an abstract linear model is ever appropriate. But a linear model might be reasonable over some range of the covariates for some values of the parameters. But reasonableness is not like a yes or no thing, it's a question of degree, and so we're putting continuous priors on the parameters to exhibit that. In this case, for plus or minus 3,200 people around the threshold that changes you from plurality to a PR system, seems pretty linear if the coefficients are small enough to keep it, between 0 and 100. So that's fine, but you got to take a position on that in advance with the prior beliefs, and then you can update that with the posterior. Second question about missing airplane. That should hopefully illustrate to you how useless the frequentist approach would be in that situation. And of course, they're using Bayesian methods rather than frequentist methods when trying to find it and whatnot. But that's because Fisher, in particular, defined probability in order to exclude the Bayesian approach, and define probability in this limited, narrow way, the proportion of times that something happens in the limit as the number of repetitions goes to infinity. And things are either true or false. We only get proportions by averaging over the trues and the falses for many, repeated. And so it sounds ridiculous, but the frequentist approach to saying what's the probability that this airplane is in the square would be to take a random sample of airplanes and count how many times, the proportion of times they end up in this square in the South Pacific Ocean. Which is none of them for any plane that you possibly could sample, but we don't need to sample airplanes because for regular airplanes, we already know where they go. Their path is already, being recorded everywhere. It's just this particular one somehow got pointed in exactly the opposite direction that it should be going, and it kept going to nowhere until it ran out of gas. And so the fact that Fisher defined probability as being, only pertaining to functions of things that the researcher can explicitly randomize means that, the frequentist approach is inapplicable to saying, where the plane is, but by extension, the frequentist approach is inapplicable to all sorts of other things where we can't do sampling, for the temperature in 100 years, or stuff like that. And these extreme abnormalities are a lot of times the things that scientists want to be able to explain. There's the whole world for a month was interested in finding that plane to try to figure out what went wrong. But the frequentist approach would not have been applicable. And so the questions ask you some basically Bayesian ideas, and as more information becomes available, pieces of the wing wash up on the coast of Africa and whatnot, you can further update your beliefs about where the plane is. But it, have not been able to update it enough to actually find the plane. But that doesn't mean the Bayesian approach has been unsuccessful. Like compared to the entire Earth, or even the entire ocean, all the oceans, to be able to say it's within like 90% probability, any like relatively small piece of the ocean, is a pretty important thing, is to be able to say, well, it must be in some ocean because it's not found on the land anywhere. But not, you know, precise enough to say exactly where it is so that it could be, you know, found so far. But somebody will probably find it eventually. And if so, they'll be using Bayesian techniques or things that resemble Bayesian techniques. Or they just get lucky or something like that. Then the last question, you know, forced you to confront the fact that the things that make this course hard are the same things that make it essentially impossible to introduce material like this in, you know, the theory and methodology class. Honestly, we're trying to give you points there because these are the things that should have occurred to you over the course of the first part of the semester, and then a lot of you gave points right back by not, you know, addressing some of the things that were mentioned on the things to include. But, you know, I think it hopefully made it clear that, or, you know, implicitly why theory and methodology doesn't have a week on, you know, what methodology you should use. Because you can't really accomplish a whole lot in a week on that question. But that sort of leaves a lot of people in the QMSS program, perhaps otherwise, who don't really know that maybe they should be learning Bayesian methods because they don't even really know what they are or how they're different from frequentist or Bayesian methods, and so it kind of compounds on itself. So anyway, the deadline for changing your grade designation, if you feel that's necessary, is today to change your grade either to pass-fail, in which case it's, you know, basically the same. It's just you don't get a specific letter grade on your transcript, but you do get credit for the course hours, or R credit, in which case you don't get course hours toward your degree. You also don't take the final exam, but you would still need to pass based on the homeworks and the discussion and the midterm. And we'll have 3 more homeworks, I guess, one starting tonight. And you know, the weights for whatever are on the syllabus if you need to do. But we'll put up the curved grades for the midterm tonight, and so you can make that decision if necessary. We talked in more detail about the answer key on Tuesday, so if you haven't seen the video for that, be sure to check it out. But are there any other questions about midterm? All right, so somewhat belatedly, let's get this started. We don't have enough time to go through that, but hopefully you've heard it already. So anyway, going back to question 1 on the midterm, if you can do that first question, the rest of the semester is really, you can see it as tweaking the generative model for different other types of outcomes, discrete outcomes, etc. Also, as we get later in the semester, different grouping structures. And then once you derive the log likelihood, if you can, and if you can't, you really shouldn't be using maximum likelihood either. You know, the rest of it is not that difficult in terms of updating your beliefs about the parameters. Some of you may have seen a notification that there's a new version of RStudio. I think this one does make it a little easier to edit QMD files, which is something that, like, you know, we're going to continue to be doing for this class. So the data that we're going to use today is in the week 09 folder. If you poll from GitHub, it's polling data at the individual level. So each row is a survey respondent, which is otherwise somewhat hard to come by. A lot of that data is private, but this was made public. And this poll was conducted the day before the 2012 election between Obama and Romney, and it asked people a bunch of things about themselves, including who do they want to win the election that would be happening the next day. And we can create all these predictor variables that we might use, gender, age, etc., are factors, they're category variables, and so when you put those into a regression in R, they get made into dummy variables. And you can do that using the model matrix function. If you just give it the formula you want to use in the data set, it will create a matrix of predictors to be used in that regression model. We can drop the first one, which is the intercept, because we're going to do the intercept business in our own way. Take the average column-wise, subtract the average from each column. But anyway, we get these now 16 columns of the design matrix X, each of which was a dummy variable before we subtracted the mean. But anyway, each column only takes 2 unique values here. And you can see there's different age categories, different income categories, different regions people are in, etc. So these are the data we're going to be using and try to predict whether the person supports Obama or Romney. Right? So, like I said, here's a generative model that in a lot of ways is very similar to what we've been doing before, even going back to when we were doing this with bowling. But it's a little bit different because the outcome in this case is binary. Do you support Obama or do you support Romney, or in general some sort of success versus failure? Success being denoted 1, failure being denoted 0. And the generative model, or a generative model for something like this, is to start by saying for each observation what we observed, the yes or no, why, is defined by y star being positive or not. So 1 if yes, 0 if not. Okay, what's y star? Y star is the sum of eta and epsilon for all n. Okay, what's epsilon? For all n, the epsilon can either be drawn from a standard normal distribution or a standard logistic distribution. If it's standard normal, we tend to say this is a probit model. If it's standard logistic, we tend to say that it's a logit model, even though those terms kind of encapsulate a bunch of stuff here that would otherwise be in common. Then, okay, if that's epsilon, what's eta? So for each value of eta, we have some linear specification with the intercept and a bunch of predictors that are weighted by their respective coefficients, and you can do what we've been doing before, substitute for alpha with gamma minus the coefficients times their means, all added up together. And then factor out the betas, and then you get gamma plus the sum of the coefficients times the deviation from the average in each of the predictors, which is actually how rstanarm does it. And then if you make gamma primitive, you need to at some point put a prior. Normal prior would be usually fine, as well as priors on each of the coefficients, beta. And so the bottom half of this is exactly the same as what we were doing when we had linear models before. It's just the top part of it, how do we observe the outcomes? We should think of these binary models as saying we observe the sign of y star, but without observing the number y star. And another way to interpret this, particularly in like an economics context, is that y star is the utility difference of person n if Obama versus Romney were elected. And so if that utility difference is positive, then they favor Obama. If that utility difference is negative, then they favor Romney in the election. So questions about that so far? All right, so that's the model. Then in terms of thinking about the priors, want to talk about the prior for the intercept a little bit later. What makes these models a little bit challenging is that the coefficients, and the intercept for that matter, are in units of eta. that's different from the linear models that we were doing before, where the linear predictor was in the same units as the outcome. But now the observed outcome is just 1 or 0. It doesn't really have units. So the coefficients are in the units of eta, and they tend to be on the smaller side for reasons we'll see in a second. But in this case, we have 16 coefficients that we need to be specifying priors on. And so, you know, we can do things like say, okay, the coefficient for men relative to women, you know, men less likely to support the Democratic candidate, etc. Then we have 5 age categories. And so we could specify a sequence of those, you know, prior means, etc. Not really sure whether suburban people are more likely to vote for Obama or Romney compared to rural people, so I could just have a prior of 0 for that, but I'm pretty sure urban people are more likely to favor Obama than rural people are. And then we could have another sequence of 5 for the income categories, you know, poorer people more likely, poor people more likely to support Obama, richer people less likely. And then for each of the 3 regions as compared to the Midwest, you know, what do I think the shifts are? I can use the same standard deviation for all of these coefficients, but this is an example of choosing the prior means in these normal priors for all these different coefficients. And then to draw from the prior predictive distribution, so 1,000 times. For each value of m, we want to draw from a normal distribution, r times, with that mean and standard deviation s, which I said before. So this will return a data frame. So dfs, map underscore dfc, returns a data frame where each call here is a column of that. And so this part right here would be 1,000 by 16 data frame. It has a column for each of the coefficients. And then I add to it a column for gamma, the intercept relative to centered predictors. That has mean M0 and standard deviation S0. So this is same idea as what we've done before, with just like a little bit of you know, using per in order to have now dealing with 16 variables. And then for each row, realization of the parameters from the prior, we want to draw from the predictive distribution. Actually, I had a little bit of trouble with this because the version of dplyr that I have installed on the computer where in my office is different from the dplyr that I have on my laptop. And so it wasn't accepting this. So this is actually only multiplying the first column by the first coefficients, set of coefficients here. Really, I would need to do like x2 times second coefficient plus x3 times third coefficient, all 16. I had like a matrix vector version of this, but it wasn't liking that on this computer. But anyway, so here's like part of eta. Then I can draw epsilon from a standard logistic distribution with number of realizations equal to the number of observations in x. Construct y star as the sum of eta and epsilon, and then derive y as the logical is y star greater than 0 or not. And so we get a table of 6 million draws that have, you know, eta, epsilon, y star, and y, and you can see where y star is positive, this is true. Where y star is negative, the outcome is false. All right. So that's how we draw from the predictive distribution. Miraculously, this came out looking reasonable, even though it wasn't actually the right distribution. So more of the mass here of y star is to the right of 0. That's reflective of our prior beliefs that people are slightly more likely to favor Obama than Romney on the eve of the election in 2012. But all the values pretty much are between -6 and 6, which is somewhat reasonable. Most of the values are between -3 and 3, which is even more reasonable for a model like this, for reasons that are not super apparent yet, but we'll circle back to. Okay, so before the midterm, we didn't really derive the log likelihood in linear models. It's fairly trivial. It's a little more complicated when the outcomes are discrete. But in the case where the outcomes are binary, there's really only one likelihood function that you could use if they're conditionally independent, and that is the Bernoulli, which we talked about a month ago or so. But the log likelihood is a function of the parameters. So what would that look like? Well, first of all, okay, so we're talking about the log likelihood here. But if the observations are conditionally independent, which for surveys makes sense, we have the probability of observing the whole data set is the probability of favoring Obama raised to the power y, which is 1 or 0, times the probability of favoring Romney raised to the power 1 minus y. And then the logarithm of a product, which you're always taking the logarithm if you're doing this on a computer or in R or whatever, turns the product into a sum of logarithms. So we have the sum over the entire data set. Bring this down, we have the log of the probability of favoring Obama plus 1 minus y times the logarithm of favoring Romney added up over the whole data set. Okay, so what's the probability of favoring Obama under the model? Well, the probability that yn is 1 is equivalent to the question, is y star greater than 0, and y star is eta plus epsilon. So it's equivalent to the question, what's the probability eta plus epsilon is positive? And so if you move eta to the other side, that's the probability that epsilon is greater than negative eta. And because the normal distribution and the logistic distribution are symmetric around 0, or the standard versions of them are, that turns out to be equivalent to what's the probability that epsilon is less than or equal to eta. So you just multiply the inequality by -1 there. And the probability of a random variable being less than or equal to something can be written as just the CDF. So F here could be either standard normal, in which case this would be a probit model, or standard logistic CDF, in which case we say this is a logit model. So anyway, we just substitute F for the probability of supporting Obama here and there, and we're good. So like I said, you can use either standard normal or standard logistic. Standard logistic CDF is elementary, whereas standard normal CDF is not. It doesn't really matter for scientific purposes, but in terms of writing it out on a slide, okay, the standard logistic CDF is 1 divided by 1 plus e to the negative eta, in which case, we can just plug that in, and now we have our log likelihood function, where eta n is this right here, which is also the logarithm of the probability of supporting Obama to the probability of supporting Romney, or the logarithm of the odds of supporting Obama. And so in the case of a logit model, eta can be interpreted as the log odds of success, whatever success is. Now, you don't have that interpretation if we use the standard normal CDF. But even if you use standard logistic CDF, make it a logit model, it's not as if the logarithm of the odds is particularly interpretable. But like we said before, beta and gamma and whatnot are in units of eta. So in a logit model, they're in units of log odds of success. And that means, rather than looking at y star, we can look at the probability view in the prior distribution by plotting eta given to the logistic CDF, P logis in R. So here we get the probability of supporting Obama, and that, because I didn't use the other 16 variable predictors, I only used the first one, doesn't vary very much. So this one actually doesn't look super reasonable, but trust me, it did look reasonable when I used all of the predictors, in that the probability was mostly going from about 0.25 to 0.75. You're slightly more likely to favor Obama than Romney, you know, etc. But a lot of times, if you use like super weakly informative priors and then you plot the prior distribution of the success probability, you get this U-shaped business that has very little probability near 0.5, and almost all its probability is right near 0 or right near 1. And really that doesn't make a whole lot of sense for a lot of social science applications. Now you might say, well, I know people for whom the probability that they supported Obama was either very close to 1 or very close to 0, but conditional only on these like 5 things: gender, age, urban density, income, and region, most notably not race. You know, just given the intersection of those things, it's really hard to say someone is like definitely Obama supporter or definitely Romney supporter. So I think the prior predicted distribution I had, not this one, but if it had compiled correctly, you know, was looking okay. All right? And so then to get the posterior distribution, we want to call the Stan-GLM function in the rstanarm package. Now, one thing that's a little bit confusing, if you give it a factor with 2 levels, it interprets the first level as 0, failure or whatever, and the second level as success. So in order to get around that, I have to redefine the outcome variable as equal to its first level, because the way I specified the priors, like Obama was success and Romney was failure, even though I could have done it the other way around if I just multiplied all my priors by -1, like it would have been the same thing. But anyway, so outcome is like true or false, do you support Obama? We're specifying that the log odds here is a linear function of these categorical variables, which R is going to again make into dummy variables when it goes to estimate this thing. What's different from what we did before is you also need to specify the family argument. So by default, family is Gaussian. So what we did before spring break was working. It was just using the default of a Gaussian likelihood. In this case, we need to use a binomial likelihood. Now remember that Bernoulli is a special case of binomial with just one trial. So if we're doing this on individual data, it is binomial just with size equal 1. But binomial is not the default. And so one way that you often make a mistake is forgetting to specify this, and then it'll use a Gaussian likelihood rather than a binomial or Bernoulli likelihood. And then what actually is the default to the binomial family is to use a logit link function, but you could also put probit in there if you wanted to have normal errors. The data set where the variables live, and then we have a prior on gamma, which is relative to centered predictors. So it's the expected log odds for someone whose predictors are all average, and then the prior on each of the betas. So this was a vector of size 16m and a scalar s, so that scalar s was used for each of those. And then again, it's better to be plotting the posterior distribution than it is to get too caught up on a particular number. However, remember, all of these intercept, well, one, remember the intercept now in the posterior distribution is alpha rather than gamma, so it's relative to the raw predictors rather than the centered predictors. But all of these are in terms of eta, which in the case of a logit model is log odds. But again, we see the log odds for a man as compared to an otherwise identical woman, having this posterior distribution shifting the log odds more negative in terms of supporting Obama. For age, older people much less likely to support Obama for some reason. And then less so on all these other variables. But there's, pretty noticeable regional difference as well. And the coefficient for people whose income is reported to be 150,000 is very uncertain because there were very few such people in the data set. And so its estimated coefficient is much less precise than, some of these other things where we had plenty of observations. All right? You can see the posterior medians in dark blue here, 50% intervals in light gray, and these, densities I think span from probably 90%, something like that. But anyway, this is a better depiction of what you've actually learned as a result of conditioning on the data than to just have like a table and say like, oh, I can't interpret any of this, but like some of these are positive, some of them are negative, some of them are statistically significant, some of them aren't, stuff like that. So questions about this or how I got that, or what the model was that implied this is the posterior distribution I am supposed to be drawing from?
If you go back to the last line of the posterior distributions, so how, again, should we be interpreting, say for like male, how does that relate versus female? Because that's like not there.
So again, this is in terms of eta, and in a logit model, eta is log odds. And so the way to interpret this correctly is to say, I don't know exactly what these numbers are, but if you have two people, one of whom is a man, the other of whom is a woman, they are the same age, they live in the same place, they have the same income, same region, whatever. The expected difference in log odds between that man and that woman is given by this distribution here, which looks like it has a median of about -0.4 or something like that. Now, you can't make an absolute statement in terms of probability because the probability of supporting Obama depends on all these other things. So if you want to say what's the difference in probability between a man and a woman who are otherwise the same supporting Obama, there would be some more work that you have to do that's not evident in this plot. But what is evident in this plot is we're very sure that the coefficient is negative for men, so they are less likely to be supporting Obama, and then the magnitude we'll have to show it another way. Yes?
So I have a question on the generative model. So in Mikko Reef, he puts the link function in the generative model, he's writing it out. Am I right in understanding that here this is sort of like a more general way of doing it, and then you specify the link function later with the likelihood function?
Yes. So this implies the same posterior distribution as what was in the reading. It looks a little bit different, but it implies the same distribution mathematically. I write it like this because it more closely resembles the linear generative model that we did before with the error term. Richard hates this because he doesn't think error terms are like particularly interpretable and things like that. So he doesn't go this route. Another reason I like this way is it's easier to then extend this to ordinal models in like 3 weeks. So when it's not just yes or no, but it's like strongly agree, whatever. So I do it this way, Richard does it his way. You could read them both. They both imply the same prior predictive distribution. So you can decide whichever one you like better. But it is cosmetic, even though it's not like immediately obvious that these are the same. But yes, you know, family link equal logit is to say I'm assuming standard logistic errors rather than standard normal errors if I put link equal probing there. Again, that's not like super obvious. Now, what if we had a slightly different generative model where observations can be clustered into groups? So we say y for group J is the sum of the y's for all observations I in the jth group. And then we just proceed as before with this being, so if the yij's are just ones or zeros, depending on whether eta plus epsilon is positive or not, then the y sub j's, which are the sum of these trues and falses, that's going to be a count between 0 and the number of observations in the jth group. So all this is the same as before. And this implies the same information. It's just when we do it in rstanarm, we're going to be actually using a binomial likelihood with trials or number of opportunities equal to the number of people in the jth group, instead of Bernoulli, where everybody is just their own individual. And so to prepare the data for doing that, it's convenient with dplyr to just make a group by statement. Now you can only do this when all of the variables are categorical, or you could possibly do it if you had some numeric variables, but they only took on a few distinct values. But in this case, all our predictors are categorical. So everyone who's a woman aged like 34, who lives in suburbia and has an income of 75,000 to 100,000 in the Midwest, all such people are going to have the same probability. So the intersection of those 5 variables defines a group. And then we can count the number of such people who support Obama in that group and every other group, defined by the intersection of those variables, and we get counts between 0 and the total number of people in that group. And then we can summarize to count up the number of people in each group who support Obama, and conversely, the complement is the number of people who support Romney. Now, one reason why you want to do this, if possible, is the grouped data has only 516 rows, whereas the original data, after excluding the NAs, has over 6,000 rows. Now, that's not really going to be that noticeable a difference here, but if you had truly huge amounts of data, being able to have 1/10 the number of rows is going to make things execute faster in standard by like a factor of 1/10. Also, it's a bit easier to check that your model is reasonable, like in the posterior predictive checks and whatnot, if you have grouped the data. So when possible, which is to say when all of your predictors are categorical, which is not uncommon in the social sciences, you probably should. So age here is age bucket rather than age number. If we had like a bunch of different ages, then we would have almost as many groups as we have observations. But in this case, age, like a lot of situations, it's a category group. So the way in which we would do this with stan GLM, and now I'm going to do it with probe it, so to assume standard normal errors rather than standard logistic errors. And when you do that, your priors should be multiplied by about 1.6 as compared to what they were in a logit model based on the difference in density at the median between a standard normal and a standard logistic. But it's going to be the same, except we have a slightly different way of specifying the outcome in a binomial model. It's actually a 2-column matrix with successes in the first position and failures in the second position, which is like reversed from the way when it's Bernoulli. But anyway, that's how it's done in GLM. And stan_GLM is like quirk for quirk compatible with GLM. It's going to be using stan to get draws from the posterior distribution rather than maximum likelihood estimates. So we say binomial with link equal probe it to assume normal errors, and we give it pooled groups rather than the raw poll. For that, priors are the same. I just multiply everything by 1.6 because I'm using probe it. And then, like I said, another reason why it's good to group your data when possible is it makes it easier to check that the posterior distribution is doing something reasonable. If you did it on the individual data, then like all the data values would be either between 0 and 1. So you just get this like line of 1s and line of 0s, and then the probability is in the middle, but you have a hard time saying like when the probability is high, are there more 1s than there are all 0s because everything gets overlapped with each other in the actual data. If you group the data, then we can compare the model's probability of supporting Obama multiplied by the number of observations in each group to the proportion of people in each group that support Obama. And so here you can see like each dot is a group or a binning of groups somehow, and we can say, okay, this looks like it's fitting pretty good. These 3 are 3 of the 4,000 realizations from the posterior distribution, so like rows of the draws of the posterior matrix. And so you can see there's some uncertainty here, but most of the points are falling within like the 90% intervals, etc. If like one doesn't, that's okay. So anyway, but this would be much harder if our data was just like 1s and 0s, as opposed to proportion of people in the group who do it. All right. So questions about that or the grouping business? It's literally the same information. I did change it from normal error or from logistic errors to normal errors, so it's slightly different. But just aggregating into groups when all of the predictors are categorical does not change the information. So if I did this with logit link, I should be getting the same posterior distribution as before if I set the same seed. There might be some numerical differences, but it's the same idea. Did you have a question? Yeah, so I just changed the errors to show you how you could. It's not a consequence of grouping the data. I could have done normal errors with the individual data. I could have done logistic errors with the group data. Like, it's your choice, etc. Okay, so now I want to talk about some 4 functions that you can call after stan_glm, which do different things, very different things, but some people still get them confused because they're sort of less clear about the underlying concepts. So as matrix or as _Tibble, whatever, is going to return a R. R by default is 4,000 times 1 plus K matrix or Tibble. The first column is going to take the draws of alpha, not gamma, alpha, in order to be compatible with GLM. So the first coefficient of GLM is the intercept relative to the raw predictors. So that's what standard GLM is returning if you give it as matrix. And then the remaining columns correspond to the k plus, or the k element of beta. So they're going to have posterior draws of beta male, beta age, whatever, age higher, all those, up to, region west, all the 16 coefficients in the model. So, we saw that on the midterm. You needed to fish out the coefficient on the PR system to say, what proportion of them is positive draws, things like that. Okay. Then the second function is called posterior underscore linpred, and that is going to return a R by N matrix, where N is the number of observations in the data after throwing away the NAs on the relevant variables, where the little n column contains draws from the posterior distribution of the so-called linear predictor, eta, which is alpha plus the sum of the coefficients times the raw predictors. So posterior distribution of eta induced by the posterior distribution of alpha and beta. So that's going to be an R by N matrix, and each column corresponds to one observation. Although if you've grouped the data, then each column is going to correspond to one group, not one person. Posterior E-pred returns an R by N matrix, where the n column contains the posterior draws of the conditional expectation of y, given the predictors. And it is obtained by applying the so-called inverse link function to the draws of eta. Now, this inverse link function is confusing because frequentists made up this terminology, and frequentist stuff is confusing. So, like a normal person would think of a function that maps eta to mu, but frequentists think of everything backwards. So they're thinking of the function that maps mu to eta as the so-called link function, but it's an increasing function. So the inverse exists. The inverse is the function mapping eta to mu, but frequentists call that the inverse link function. Whereas if Bayesians were making up the terminology, we'd probably call it something else. But in any event, like in a logit model, it's like applying the logit CDF to eta. You get mu, and mu is the conditional expectation of the yes-no outcome, and so it's going to be between 0 and 1, indicating in this case person n's probability of favoring Obama. And then posterior predict is also an R by N matrix, where the nth column contains posterior predictive draws of the outcome for the nth person or group, conditional on mu. So in the case of Bernoulli, it's drawing from a Bernoulli distribution with that person's mu. So that could be like 0.7 or something. The mu could be 0.7. But a draw from a Bernoulli distribution is either going to be ones or zeros. And so that's one of the things that makes Bayesians different from other people. When Bayesians say this is a prediction, it had better damn well be in the sample space of the outcome. So if the outcomes are 1 and zeros, the predictions have to be 1 or zeros. What other people often refer to as predictions more closely resembles what Bayesians would call the expectation of the predictions. So you'll see like a lot of supervised learning or stuff like that say, my prediction for this like yes-no variable is 0.7, even though 0.7 is not even a possible value for something that's binary. But that more closely resembles what we would call an expectation of the outcome. When we say prediction, it's in the same sample space as the original outcome is defined in. So if this is like a binomial model with groups, then the prediction is going to be an integer between 0 and the number of people in that group, not some like 7.4 business. Right? Okay, so any questions about these 4 functions? Now, this poll from the day before the election in 2012 was intended ostensibly to be representative of all adults in the United States, whereas it's much more common when doing a poll like right before the election to try to do a poll of likely voters, because you're trying to anticipate what the election will be. And so adults includes voters and people who aren't even citizens, but are adults, and then some citizens who choose not to vote, or maybe aren't even registered to vote in their state, something like that. So different population as compared to a more typical poll that would have been done on the eve of a presidential election. But it probably didn't do a very good job of even being representative of all adults, because it was conducted online, actually by Google. So like Google made a Google form, and like anybody can fill it out. So one, maybe not everybody was actually 18, but two, like even if you could manage that somehow, it wouldn't be really representative of all U.S. adults, because any poll that's done over the internet, it's going to pick up fewer old people, for example, and it's going to have over-representation of young people. It's going to have over-representation of people who at least have like enough money to afford internet, and underrepresent or afford internet on their smartphone, and underrepresent people who don't have like continuous access to the internet, and other things like that. Also, one sort of extraordinarily common finding for polls like this, much more likely to include women than men. So this poll came out like 2/3 women. But it also has a lot of missingness. So like even if the poll was like perfectly representative of the population that they were trying to make inferences about in terms of who they contacted, well, if people don't respond to the question like what's your gender, what's your age, what's your income, or whatever, the distribution of the people whose data is observed and not missing is going to be not necessarily representative of the intended population, etc. And so this sort of thing happens a lot. But suppose you wanted to make an inference about the population of all U.S. adults. What can you do? Well, first thing you can do is to call expand_grid, passing to it the levels of all the variables that you want to condition on. So this was 2012, so gender just had 2 levels. Nowadays, most polls will have like male, female, and other, so there would probably be 3, 6 age categories, 3 urban density thing for rural, suburban, urban, 6 categories of income, and 4 regions. So you intersect all those together, you get 864 types of people as far as this model is concerned. And so now you can get a data frame with 864 rows. And then if you pass that to posterior linpred with new data is that, you would get the posterior distribution of eta, conditional on these 864 types of people. So that'd be 4,000 by 864. And then if you apply the p-norm function, which is the inverse link function to that, you would get the probability for each of these 864 types of people of supporting Obama over Romney. And then, so let's call that mu. It's going to be 4,000 by 864. And then if you go to the census data and get the number of people in each of these 864 strata who are adults in the population, and you matrix vector multiply mu by the counts of the number of applicable adults in the population to that. So if you don't know matrix vector multiplication, it's just like take the first row of mu and then weight it by each of the 864 types of people in the population, and then add all that up. And then second row, same thing. Third row, same thing. And so what you end up in the end is to get a 4,000 by 1 vector of the expected number of people in the population, so all adults, who favor Obama over Romney. And you could say, like, you know, it's, I don't know what it would have been in 2012, like 160 million to 140 million or something like that. All right, to make that inference about the population. But in order to do that, you need to know what the population you're trying to get at is, which is difficult when you're trying to make inference about the population of likely voters, because we don't know who is an actual voter until after the election happens. Like, we know you have to be a citizen, that's a necessary condition, and you have to be, in most places, registered to vote, that's another necessary condition. But kind of the main challenge with polling is to figure out who among the registered voters is actually going to vote. We already know, based on your demographics, like, what is the probability you would vote for the Republican or the Democrat or whatever if you're, like, you know, male, 32, live in the South or whatever. We know that pretty well. What we don't know is if you or whoever that guy is actually going to show up to vote. And that's really where most of the uncertainty in polling happens. This model that each pollster has, and it's a little bit different, and often it's like a secret as to how they estimate whether someone is or is not a likely voter. But anyway, if we're just trying to make inference about adults, the census data is extraordinarily reliable for that. And so we could do this to make that inference, even though the data that we had was in many ways not representative of the population of adults. The assumption we're relying on here is that for the people in the poll who are male, age 30 to 35, live in a city, income is 40 to 60,000, and they're in the Northeast or whatever, the people in the poll who fit that description need to be representative of those same people in the population. So it's not as if, like, the people that we have that are in one of these 864 groups, they don't differ on some other variable from people in the population systematically. And so it would be nice if we had race also to condition on, but this data set didn't ask about that. But anyway, so this is an example of something called post-stratification, which we'll talk about more toward the end of the semester. It's particularly helpful in multi-level models, but is extremely different from what frequentists do, which is use weighting of the sample data. They reweight the sample data to change the estimator to try to make the maximum likelihood estimator like representative of the population. Here, Bayesians, we just get the posterior distribution for the data that we have, and then we predict in the population that we're interested in, if we're trying to make some inference about a grander population. And so it doesn't matter if there's like way too many women in the data set as compared to the population, as long as the women in the data set are representative of the women in the population, when you take into account the other 4 variables as well. So even if your data set is like off, if the people are representative of the people in their group in the population, you can get good inferences about that population using the posterior underscore whatever functions. Questions about that? Yes?
Can you just hit on what mu is again?
Okay, so again, inside out, posterior linpred returns an R by N matrix with the posterior distribution of eta. This was a probit model, so we use standard normal CDF as the inverse link function. So standard normal CDF applied to eta returns mu. the probability of someone in each of these 864 groups supporting Obama. So that's going to be a real number between 0 and 1, exclusive of 0 and 1, in the middle somewhere. Okay, so that's going to be 4,000 draws on 864 types of people. If we weight that by the number of actual adults in the population who fall in each of these 864 strata, and use that to matrix multiply mu by, we get a posterior distribution of the expected number of Obama supporters among all adults in the population. And that was one reason, going back a long way now, to why I in my prior started by thinking about 55% of adults support Obama over Romney, because that was more extreme than what the actual vote came out, which was like 52-48, something like that, among voters. But if you also think about people who don't vote, either because they're not citizens or because they're citizens who don't turn out to vote, those are usually going to be poorer people. Poorer people are usually less likely to support the former chief or whatever of Bain Capital, who's also governor of Massachusetts and whatnot, but Mitt Romney. So anyway, I thought about 55% of adults would support Obama over Romney. And then I used the Q-logis function, which is the inverse of the CDF, to map that into log odds for my prior on gamma, the intercept relative to centered predictors. And so sort of your thoughts about the log odds in the population correspond to your beliefs about gamma. Okay, good questions, good questions. Anything else about this? Yes?
You know there are any differences in link and predict?
Yes. So you can think of these four functions like the fourth calls the third, and the third calls the second, and the second calls the first. So the first returns the posterior draws on the parameters, albeit alpha rather than gamma. The second one, posterior limpret, uses the posterior draws of the parameters and the x's you give it to yield you the posterior distribution of eta, which is this linear form here. So eta is the symbol for the linear predictor. But in a generalized linear model, which is to say not really linear, there's an inverse link function mapping eta to the expectation of the outcome. So that's standard normal, standard logistic CDF applied to eta yields mu. And then posterior predict is going to return draws from the posterior predictive distribution given mu. It's going to draw from a Bernoulli or a binomial or whatever the appropriate distribution is to yield discrete predictions that also take into account the randomness and the error for your voting patterns, etc. So the difference between the second and the fourth is, well, the second one is the posterior distribution of an intermediate parameter eta, and then the fourth is going to be in the units of the outcome.
Yeah. How would you, like, do you have a similar function but instead for like continuous variables? Or continuous
Oh yeah. So if the outcome was continuous, posterior predict will be producing continuous predictions. So this also would have worked before the midterm. But posterior predict is going to include the epsilon, whereas posterior epred is returning mu. It has nothing to do with the epsilon. So in a continuous case, posterior epred differs from posterior predict by the realization of the error term. And it draws the error terms new from like a normal distribution if you had normal likelihood. Question?
How is, so in that code, you you apply P norm to the output of posterior limb thread. How does
Yes.
that differ from posterior apron?
In a binomial model, so as opposed to Bernoulli, the expectation of the outcome would be not between 0 and 1, it would be between 0 and the number of people in the group. So here, I wanted to do it back on the individual level. So just give me eta, which is log odds, and then I'm going to apply my inverse league function to eta. That gives me the expectation of an individual. Then I weight my number of individuals in that group in the population to give me my Obama posterior distribution among population of adults. But if I had done this on the individual data, Bernoulli, then posterior EPRED would be equivalent to P logis, because I did it before with the logis model on Limbred. All right, good. Okay, any more questions about like Bernoulli binomial sorts of models where the outcome is like success failure, possibly counted among people in a group? Okay. So now let's switch to another data set. This is something that was used for teaching. It has a weird URL that you could type in if you want to, so I'll leave that up. So this is data on where the outcome variable is the number of times that videos on YouTube have been watched. These 50 videos in the data set are on scoliosis, which is like a disease that makes your spine like not straight in children or whatever. Yeah, so not particularly like social science, but it was a small data set that I could easily, download with count of the number of times each of these videos were viewed. SCOL somehow is a measure of the scientific accuracy of the video as assessed by an actual doctor, or maybe multiple doctors, I don't know. And then age 2 is somehow different from age, but age 2 is the number of days that said video had been available on YouTube for public viewing. And remember from what we did a while back ago, the Poisson distribution can be derived from the binomial distribution by letting the number of trials go to infinity while keeping the expected count fixed and finite. So remember we did that thing where number of trials goes to infinity, success probability goes to 0, exactly the same rate, so that success probability times number of trials, which is the expectation, stays fixed. And that's how we get the Poisson distribution from the binomial distribution. And the Poisson distribution can be applied to situations in which we have count outcomes, like here, the count of the number of people who watch these videos, when there is no explicit upper bound on the number of counts, or which is to say, like every person in the world who has access to the internet, they all have a small chance of watching a video on scoliosis. And then we want to model the number of people who actually watch these videos, and to model it as a function of the scientific accuracy thereof. So yeah, a lot of interest in these like social media impressions, for better or for worse. So what would be like a generative model for counts? Let's start by saying the count is drawn from a Poisson distribution with expectation mu n times epsilon n. And that's true for each of the n, little n videos in the data set. So each video has a different expectation, and that expectation is the product of mu n and epsilon n. Okie dokie. What's the distribution of epsilon? Let's say it's gamma with shape phi and rate phi. Okay, what's the distribution of phi? Phi we're going to say is epsilon exponential with rate r, or expectation 1 over r. Okay, so what's mu? Well, for all mu, or for all n, mu is going to be defined as the antilog of eta, e raised to the power of the corresponding eta. Okay, what's eta? Well, eta has a linear form, intercept, plus possibly a so-called offset, which was talked a little bit about in the reading, plus the weighted sum of the differences between the predictor and their expectation. So offset, you can think of it as a variable that has a coefficient that is fixed to be 1. And so if you subtract offset from both sides of the equation, you get eta minus offset is equal to gamma plus the weighted sum of the predictors by the coefficients. And so what including an offset does is essentially to change the units from video views to, in this case, video views per day, because we're going to use age 2 or the logarithm thereof as an offset. And so it changes the units that we're thinking about gamma and beta of being from log views to log of the ratio views per day. And that usually makes it easier to think about prior for coefficients and intercept and whatnot. In terms of like expected log count per time rather than just like what you see on YouTube, which is like the number of times that this thing has been viewed. So anyway, you will often see offset be some sort of a duration or like time or number of opportunities for the outcome to happen. But the rest of it is really kind of the same form that we did for a logit model. But we have a different inverse link function. So now the inverse link function is e raised to the power of eta instead of like standard normal CDF applied to eta. And thus, we can think of the units of gamma and beta as being the logarithm of the expected count per day. And so we're going to need to choose priors on gamma and beta accordingly in those units of eta minus offset. All right. Questions about that? Yeah.
So maybe it's a different question, but
No.
like, do we include every parameter to have like distribution rates necessarily,
Each parameter, yes.
or ways,
Yes.
except epsilon?
Epsilon has a distribution.
Oh.
Frequentists would say epsilon is not a parameter. Bayesians would just say like, okay, all this stuff is unknown. We have prior distributions that reflect our beliefs about it, etc. But epsilon does have a distribution attached to it. In this case, we're assuming gamma with shape and rate both equal to phi. But we're going to need a distribution on phi as well, because it's also unknown. So the way I write these things, everything that's a Greek letter is an unknown. But even the y's, like they're drawn from the distribution if they're not known yet. So this is an exercise we do before conditioning on the data to say how we think the data are generated, to make sure that that looks reasonable before we start conditioning on it. Okay, so in terms of the R code to simulate from this model, we make the offset, that has to be the logarithm of the number of days to apply what frequentists would call the link function to days in order to put it in the right units. And then we have x, just one x in this case, the accuracy thing. we take the average of that to be x bar. And then we draw parameters, gamma, beta, and phi. So again, I'm thinking of this in terms of, or for gamma and beta especially, the logarithm in units of logarithm of counts per day. So like e to the 5 might be like a reasonable number of people who watch, or times watching the video at a day. Something like that. And in generalized linear models, I guess maybe I forgot to dwell on this back when we were doing the binomial one, so I won't go back. In a manner of speaking, it's easier to choose the priors because the reasonable range is so small. Because we're using the anti-log inverse link function here, if eta is like 10, e to the 10 is some huge, like a trillion number. So, you know, we know that eta has to be either negative or just very slightly positive. And so we need to be choosing the intercept in the priors on the parameters accordingly to make eta in a reasonable range. And what we saw with the logit model, and like I put up the y star and it was mostly between -6 and 6, like that's kind of a reasonable range for a log odds. Technically, it goes off to positive infinity and negative infinity. But like the logit CDF up at -4 is already like 1%. And -3 is like 2%, something like that. So in order to have interior probabilities, the log odds basically needs to be between like -5 and 5. Anything beyond that is essentially to say like I'm certain it's 1 or I'm certain it's 0. With these count models, you know, the anti-log, it's a rapidly increasing transformation. So for negative values, the anti-log is going to be pretty close to 0. But like I said, even e to the 10th is like a trillion. Gonna have to sign it again. But look at the code for this and think if you have any questions. So we take realizations of all the parameters and then do row rise. So for each realization of the parameter draws, we construct eta according to that there. We construct mu by anti-logging eta. We draw epsilon from a gamma distribution. So these errors are multiplicative rather than additive. But a gamma distribution with shape phi and rate phi is going to have an expectation of 1. And it's independent of mu. So multiplying by mu by something that's random and independent but has an expectation of 1 doesn't change the expectation. It just changes the variance. And then we're done. So let me sign into the computer again. Think if you had any questions about that generative process. Okay. Questions? Yes?
So the betas are all normal with NK cascade. So like right now they're sort of set up to all be the same distribution right there, but like could we set them up to be like k different distributions?
Yeah, in principle, yes.
Okay.
rstanarm does not allow you to do that because it's sort of rare that someone would want to. It's really rare that someone even doesn't just use the defaults, even though you should not. But yeah, I think like 95% of the time people just use the defaults of rstanarm. But we're going to learn VRMS in a couple weeks, and that does allow you to specify different distributions, not just different means and standard deviations, on the coefficients and also all the other parameters as well. So did that run? Good? Yes, okay. So allow So as I was saying, okay, so we got code to draw from this generative model of the counts. Now we need to derive the log likelihood function that's implied by this generative model. Oh, question.
Because we have the offset, we're setting our priors on gamma and beta to be like the daily rate.
Yes.
Okay. But if there was no offset,
Then it would just be like the raw log count. Yes.
And so kind of implicit in that is we're assuming like the rate in any particular day is going to be the same.
Right.
Saturday.
So,
the same
yeah.
on Friday.
We could, if we had data on how many times it was viewed on a particular day, which you can't get from YouTube, at least for your own channel, then we could see like, is there a day of the week effect or whatever. Here we're just trying to keep it somewhat simple. Wanted to say something, forgot what it was. Yeah. All right. So remember, rstanarm is going to use the same likelihood functions that frequentists use. Oh, first we need to make a plot. So it's pretty easy to overdo it in a count model. So this is on the log 10 scale here. I don't really think it's possible for a video on scoliosis to have 10 to the 10th views, but the model is putting a little bit of probability on it. Now, most of it is in the like a few thousand range, which sounds way more reasonable than like 10 billion. So, like 10 billion is like baby shark territory. So because of the rapidly increasing anti-log inverse link function, you can get posterior predictions that are way too big. So I should have probably changed this one a little bit, but I wanted to show how what seems like reasonable priors on the coefficients with the offset and with the anti-log inverse link function can quickly imply at least some small probability of some ridiculously large counts for a video on scoliosis. But this is not horrible. Could be better. Okay, deriving the log likelihood. So the likelihood is just the product of conditionally independent. So it's assuming that these videos are conditionally independent, even though if you watch one video on scoliosis, then YouTube is going to suggest to you a bunch of more videos on scoliosis because it thinks you like watching videos on scoliosis or whatever. So the assumption that these videos are conditionally independent of each other is a little bit dubious in this case, but let's just go with it for now. And so with the Poisson, it takes this form with the expectation raised to the power y, e raised to the power negative expectation divided by y factorial. But assuming them to be conditionally independent, the likelihood of the whole data set is just the product of all those. Now, frequentist Stan could actually just do that, and it would estimate the posterior distribution of gamma, beta, and all the epsilons. It wouldn't even really be that much of a problem. But it is a big problem for frequentist software, because there is no maximum likelihood of the epsilons. And so what frequentists do is marginalize. They take the epsilons out of the likelihood function using integration, and then they take the logarithm of that to get to the log likelihood function. So they need to evaluate this integral here, which actually is possible to integrate out the epsilons. You can combine this term with that term, and combine this term with the other term, and it actually turns out that this integral, it's doable except the special function gamma, which like I said before is a continuous generalization of the factorial function, pops up here. And this is the so-called negative binomial probability mass function multiplied over all n observations that we sort of derived before. And so this is the likelihood function for the parameters irrespective of the epsilons, but under the model. And so it depends on the distribution of the epsilons, and which is gamma with shape and rate equal to phi. Now you might say, this thing that the frequentists are doing that sounds awfully Bayesian. And the frequentists would say, no, of course not. Because to them, epsilon sub n is a random variable. It's random because which epsilon you get depends on which observation you randomly sample from the population. And so the epsilon attached to the nth video is a random variable if you randomly select videos from YouTube. Now, in this case, I don't think the 50 videos on scoliosis were a random sample of videos on YouTube, or even a random sample of scoliosis videos on YouTube. The guy probably just clicked until he got bored and then got the data. But from frequentist perspective, it's not their fault that the researcher didn't take a random sample. Now, from a Bayesian perspective, we just condition on the data we observe. It's not required to be a random sample. But since we're not really interested in the epsilons substantively, and if we were to integrate them out, then it would mean it's less work for Stan to do. So now we're drawing from a posterior distribution with 3 parameters instead of n plus 3 parameters, which could be a little bit prohibitive if it was huge. Here, n is only 50, wouldn't have been a big deal, but n could be 50 million, in which case that could be a little bit of a problem. So anyway, since this is the first good idea frequentists have had in the last 100 years, we'll just go with it in rstanarm. Also integrate out the epsilons and use the log likelihood of the negative binomial to draw from the posterior distribution of gamma, beta, and phi. Except actually in the posterior distribution, it comes out alpha instead of gamma. So in order to do that, you can call the stan_glm.nb function, which emulates a function called glm.nb in the mass package. Or you can call stan_glm with family neg binomial 2 link equal log. That's what they do in Bayes' rule. It ends up being the same thing. So here we're modeling views as a function of the offset, which is the log of the H2, and the scientific accuracy of the video, same priors that we had before. And we can plot the posterior distribution of the remaining parameters, the intercept, which is alpha, not gamma, the coefficient on scientific accuracy, and the coefficient on, or the reciprocal dispersion, which is what we've been calling phi in this. And so there is no epsilon because the epsilons have been integrated out. And so when we say irrespective of epsilon, it doesn't mean ignoring epsilon. It means doing an integral to get rid of epsilon. And consequently, our beliefs about alpha and beta and phi are averaged over the possible values for epsilon as we integrate them. And as we can see from this posterior distribution, the coefficient on the scientific accuracy thing is negative. Now again, this is in units of logarithm of views per day. But in any event, negative means less views per day. So the more scientifically accurate the video on scoliosis is, the less it gets viewed, and the more inaccurate it is, the more it gets viewed. And this is a fairly common phenomenon on YouTube, whether we're talking about vaccines or like anything medical or like news or whatever, stuff that is not accurate gets prioritized by the algorithm, clicked by more people, etc. So, might also explain why I have like 17 followers on my YouTube, because these videos are very accurate, and so no one watches, etc. But we have a low value of phi. So if phi were infinity, so remember the variance of the gamma distribution is 1 over phi if the shape and rate are both phi. So if phi goes to infinity, then the variance of the epsilon goes to 0, and so they all get concentrated on 1. And so we would just be multiplying 1 by mu in this. And so the Poisson, the regular Poisson, is a limiting case of negative binomial as phi gets large. And so in that sense, particularly in social science, should really just be using the negative binomial because it includes as a limiting case the Poisson. And most of the time in the count models, there is over dispersion, so more conditional variance than what is supported by the regular Poisson. That's why we need to introduce the error term here. But if the reciprocal dispersion was large, then it wouldn't have really made a difference. But in this case, the reciprocal dispersion is around 1. So much less than infinity. And that implies that there's massive over dispersion in videos view counts, which is not surprising. Like some videos go viral, others don't. There's no real reason why, but you can get huge counts for some things, not huge counts for other things, etc. So if we say like, why doesn't Google do something, only put very accurate videos up somehow, whatever. So we can ask the question, well, what if all videos were as accurate as the most accurate video? What would the prediction views be? Let's say relative to the number of views those videos have now, so to put it in proportion terms. You see when you do that, most of those videos would have much fewer views if they were as accurate as the most accurate video. But the over dispersion is so drastic, which is to say the reciprocal over dispersion is so small, that some videos might randomly get a lot more views if they were more accurate. But most of these videos are getting fewer views if they were as accurate as the most accurate video. But again, this is in relative terms. Okay, so that's all we have for today. I will post the next homework tonight. I will post the curved grades of the midterm tonight. Remember, if you want to change your grade designation to pass, fail, or R credit, you need to do so on the SSOL website, probably before 9 o'clock. And that's it. And we'll have recitation office hours as usual on Tuesday.